All right, I want to make a couple of remarks and then we'll end our conversation about lines with one more example. So first of all, sometimes we want an equation for the line segment between 2 points. I don't necessarily want the full never-ending line. I want a segment. And so how do you do that? Well, let me show you. So let's say that I want the line segment between P0 and P1. And in most of the contexts that we look at, you're going to care whether you start at P0 and go to P1 or whether you start at P1 and go to P0. And so the way that I'm going to show you is how you would do it to go from P0 to P1. And so let's fill in that line, and then here's how you do it. So we're going to begin by setting our direction vector V as the vector from P1 to P0. All right, and then I need to know a point on the line. Well, you can pick either one of these, but you want to pick the starting point. So for me, R0, my point on the line is P0 written in vector form. So that's the notation that I'll use there. And then it's the same formula as before. R of t is R0 plus t times v. And if you think about it, nothing has changed the way that I've written it. And if I don't add something else, then somehow this is going to give me the full line, not just the line segment. And so here's the catch. You need to restrict t. If you restrict t now only from 0 to 1, then these two equations together give you the line segment starting at P0, ending at P1. So let me show you. So R of 0, for example, is R0. So when you plug in t equals 0, you're sitting here. And if you plug in t equals 0.5, you're going to be somewhere in the middle, and then when you plug in t equals 1, you're going to be right there. So this R of t actually traces it out. So we'll use this later, and I'll show it to you again when we use it, but I wanted to go ahead and highlight it here just so that you've seen it. It's basically the same equation that we've been using. I'm just restricting my t values, and I'm being careful how I pick my points. All right, second remark that I want to make is that two lines are parallel if and only if their direction vectors are parallel, or that's the same thing as saying if and only if their direction vectors are constant multiples of one another. And for the record, that's the same thing as saying the cross product of their direction vectors is 0, in case you want to think of it that way. All right, so there's that, and then also two non-parallel lines that don't intersect. They're not parallel. We call those skew. We'll see this on Mathematica in just a minute. So let's determine if the following lines are parallel, intersecting, or skew. And so first off, notice that I've used a different variable for each line. That's important. So the first line is all in terms of t. The second line is all in terms of p. If you use the same variable, bad things can happen to you. All right, so let's ask ourselves, are these lines parallel? And to see that, I need to be able to write down the direction vector of each line. So why don't you pause the video and see if you, without doing hardly any work at all, can write down the direction vector for the first line and then for the second line. So for the first line, the direction vector is just 5, -2, and 3. I'm just reading off those numbers, and the second direction vector is 3, -1, and 4. And so it's pretty easy to see that these guys are not constant multiple, so these lines are not parallel. All right, so we've got that down, so we know that they're not parallel. What about intersecting? Maybe they actually cross somewhere. If they cross, then that means that there is a point x, y, z that lies on both of these lines. So it satisfies this line and this line. And if x is the same at that point, then I can equate this, and I can equate the y's, and I can equate the z's. And so when I'm looking to see if this line intersects, I get a system of two variables and 3 equations. So 3 plus 5t equals 4 plus 3p, that's the x's. Then I'm going to equate the y's. 8 minus 2t is 1 minus p. Then I'm going to equate the z's. 1 plus 3t is 14 plus 4p. And sometimes it's convenient to label these equations. That's equation 1, equation 2, equation 3. That's just me labeling these guys. Okay, so at this point, when you want to solve a system like this, pick any two. You could pick these two, or these two, or you could pick those two. Any two that you want to pick, that's fine, and solve that system. Let's actually say that. Whoops. So pick any two and solve, and then you want to plug in to the third equation. And so that's the general steps. Let's actually do it. So if we were to pick equations 1 and equations 2, so you're now solving this system of equations. You should be able to do that. Linear system of equations, 2 unknowns, 2 equations. This is just linear algebra or something even that you've seen in college algebra. So solve 1 and 2. Why don't you pause the video and do that yourself? Make sure you can do that. And when you do, you should get t equals 20 and p equals 33. So if you got that, give yourself a high five. So now you just simply plug that into the third equation. And so you get 1 plus 60, because I'm plugging in 3 times 20, equals, the statement is that's equal to 14 times 4 times 33. And it's pretty easy to see that's not the case. On the left side, you get 61. On this side, you get what? 132, and 14 is what? 146. Those are not equal. So these lines do not intersect. If they did intersect, when you solve any two, you would be able to plug that into the third equation and get the same thing on both sides. Can't do that here. So these lines do not intersect, so we should end our statement with a complete sentence. We'll say, thus, these lines are skew. All right, so let's go ahead and switch to Mathematica, and I want to show you a graph of this so you can see what's going on.
All right, so I've got our 2 lines, gone ahead and typed them into Mathematica. I want to graph these lines at the same time along with the coordinate axes, which I've already typed in and entered. So the easiest way to do that is to use the show command, and you just say show and then the names of each of your graphics. But real quick, I'm using parametric plot 3D, and then I just type in each, here's my x equals 3 plus 5t, my y component, my z component, and then I went ahead and told it where the origin was just to make sure we're clear. And then iPad, I used p as the third, as the second variable. Here I'm using s. It's fine either way, doesn't matter. So we'll just run those 2 graphs. I've already run coordinate axes, so I can click show now, and it spits it out. And so, you know, at a glance, it looks like those lines do intersect. It sure looks like they cross to me, but if we grab this thing and we spin it around, all of a sudden we can see, oh, they don't actually intersect. They are skew. Looking down, you can see that they're never going to cross each other. So that's an example of skew lines, and now you know how you can figure that out.